So welcome back to this channel. Here we are going to give a full details of what they call chemical equilibrium within few minutes, and then we also look at how to apply this to our major examinations, how to solve major problems. You see, whenever we talk about chemical equilibrium, the term equilibrium is gotten from an English word that means equal, and equal means a state of balance. So imagine when chemicals are in state of balance, that means we have to have two kinds of chemicals before we can talk about balance. One thing cannot be balanced now. So two things should be balanced. So that means here we are talking about a special type of chemical reaction that it will go to the right and also go to the left. Meaning, if I add A to B must be added such that they can make C and D. Then C and D must also be added to give me back A and B. We call this kind of chemical reaction, we call it a reversible reaction. So before we can have what we call equilibrium in chemistry, there must be, number one, the reaction that we are talking about must be a reversible reaction. And how do we denote that? We have A, then we add it to another reagent B, then we are going to use half of the arrow. Then the other way too, we use half of the arrow, and we get C plus D. The term chemical equilibrium can be well pronounced here because A and B, they are reactants, and they are giving me another product now, C and D. C and D are also reactants, and they can also give me A and B. So it means that before we can actually reach what we call chemical equilibrium, it's a condition. We must, number one, before we can think about reaching what we call chemical equilibrium, our reaction must be a reversible reaction, the one that can go front and come back. I will call it here left and I'll call here right. I'm going to call here my reactants and here product. Here will also be reactants and here will be products, depending on the direction that I'm following. So you can see now that I am already having two in one reaction here. So that means that some conditions must be obeyed before a system can get to chemical equilibrium. Number one, the reaction must be a reversible reaction. So number one, the reaction must be a reversible reaction. Number two condition is that the reaction must occur in a closed system. The reaction must occur in a closed system. If you carry out the reaction in a closed system, this will help us because let's make an assumption. Let's imagine that A is a solid, B is a liquid, C is an aqueous content, and D is a gas. If you now do this reaction in an open space, what do you think is going to happen to D? It will escape and run away. So you must make use of a closed system so that none of the reactant or the products will be able to escape. So that's why we must do the reaction in a closed system. Number three condition that we have is that the kind of reaction that we are talking about, if you want it to be equal, the rate, like the time it's taken for this guy to be forming this product, it must also be the same time that this guy too will be formed. Meaning that the rate of this reaction in forward must also be equal to the rate of this reaction when we are coming back. So therefore, the next condition is that the rate of forward reaction, I call left to right forward, of forward reaction must be equal to the rate of the backward reaction. If these conditions are not met, the reaction can never get to a state of equilibrium. Another condition that we are going to look at is something that we call Gibbs free energy. So in this case, I need to tell you one or two things. Generally, as I am, as a matter, as you are, as your pen is, as your book, as everything we have in the world are, as everybody, as we are all are, or whatever substance we are, we must have a particular amount of energy that we have in all our body. For instance, this guy has energy. All the sum of all the energy that is present in the body of this guy is what we call its enthalpy. My enthalpy. Everybody have some total of all the energies that they have in their body. And this energy can be used to do two things. you can take an assumption that all the energy that you have in your body is like your time in school. Now imagine you are in a school. You can actually spend your time in two ways. You might waste majority of your time and use minority of your time to study, or you might spend majority and the other way. So that means that all the time that you have will be used to do two things: useful work, useless work. All the energy that you have in your body too, as a substance, you will use some of them to do useful work and use some of them to do useless work. Now let's communicate with some of our friends that are in a region that is very, very cold. You see, most of the time their energies are being conserved. They fold their hands. Most times they are not doing much work. They hide somewhere. They are not spending their energy. If temperature goes up, then you have to blow yourself, you have to look for a fan, you have to do this, you have to do that. You are spending a lot of energy at that point. You are not settled. So the more the temperature, the more you waste your energy. Therefore, the scientists now believe that if I call enthalpy and I denote my enthalpy with a symbol like this, but it's a state function, meaning that it can change from one state to another. I therefore say that because it's a state function, it can change. If my enthalpy now, if every energy that I have in my body called enthalpy, I use some of them to do useful work, while the other are doing what? Useless work. The one that I use to do useful work, I honor one of our uncle called Gibbs. So I therefore say that change in enthalpy is equals to change in Gibbs free energy. This Gibbs free energy is the useful work done, plus the useless work that you are going to do now, meaning you will not be settled, you will be doing randomly, you will be moving up and down. So your state of randomness or your state of disorderness is what we call entropy, and the symbol is S. We use this guy because it's also a state function to show, but this guy greatly depends on absolute temperature in Kelvin. So therefore, we now say temperature times change in entropy. So this is the value of all the energy that you have in your body. Now we are fighting between these two guys. If I am doing more useless work than the total energy I have in my body, that means the content of this term that we have here will be more than this term. Imagine when this term is more than this term, what will happen? Let's try to use arithmetics. Let's make here to be 5 equals to changing this energy, and let's make here to be 7. What do you think is going to happen? The change in this free energy is going to be, send this one here, minus 2. When this guy is negative, you are doing much more useless work. When you are doing that useless work, you can do things on your own. You are like, you can now do something that you're not in a state whereby I can now say you are now spontaneous. You are spontaneous when you have more useless work. An example of that is if I keep my marker up here and I decide to go and take my lunch in UK tomorrow. From UK, I decide to go to Russia. By the time I come back and I do not allow anybody to come into this lecture theater, I now meet my marker on the floor. I will not be surprised, because it is possible for my pen to fall down all by itself. Anything that can happen all by itself is said to be spontaneous. But if I keep my marker here on the floor, and I come back and I meet my pen up, then I believe that somebody must have assisted this my pen in going from the floor up, because it can never ever happen on its own. Anything that cannot happen on its own is said to be non-spontaneous. When will I be having a situation of non-spontaneous? That is when all my useless work is not up to my actual, original, and useful energy. Let's illustrate that using figures. Let's assume that all the energy I have in me is 5. I now say, what is my Gibbs free energy? I now say plus, let's say the useless work I've done is 3. Then by the time I transfer 3 here, my change in Gibbs free energy is going to be positive 2. or greater than 0. In this system, I will say that the system is non-spontaneous, or the reaction is not visible. But here, the reaction is visible. Why? Because it can occur on its own. But this can never occur on its own. But what do you think is going to happen? When my change in Gibbs free energy, when my change in enthalpy equals to the useless work I have done, equals to my temperature change in entropy, S. If this term equals to this term, if here is 5 and here is 5, what will happen to your Gibbs free energy? The value we are going to get will be 0. And when you get 0, the system is not spontaneous and it is also not non-spontaneous. So the system is in between the two. You can now say that such system is in what? Equilibrium. That means that one of the conditions before we can attain what we call chemical equilibrium is that our change in Gibbs free energy must be equal to 0. But when it's greater than 0, it is said to be non-spontaneous or not visible. When it's less than 0, it is said to be spontaneous. Or when it's negative, it's spontaneous or the reaction is visible. So this is all I want to just tell you about this simple illustration. Now, we can see what we have discussed now. For chemical equilibrium to occur, there are certain conditions. Number 1, the reaction must be a reversible reaction. Number 2, the reaction must occur in a closed system. We know why now. So that the gaseous product or reactor will not escape. The rate of forward reaction must be equal to rate of backward reaction. This makes a lot of sense because that is when you can think about equilibrium. And now, we now say that the change in Gibbs free energy must be equal to 0, which I try to illustrate to some extent using this enthalpy equals to change in Gibbs free energy plus temperature, also temperature in Kelvin times change in entropy. So, among all the conditions that we have stated, I now want to give an hypothetical equation that is an illustrative chemical reaction that is a reversible reaction just like this. And I'm going to apply this guide that I wrote here, this third condition. What's that condition? The rate of the forward reaction must be equal to the rate of the backward reaction. So we are going to lay emphasis on that fact. The rate of forward reaction must be equal to rate of the backward reaction. So if I write anything now, and the reaction is a reversible reaction, such as, let's say A plus B, let's say it's giving us in a reversible way, it's giving us C and it's giving us D. Let's put X mole here, Y mole, Z mole, and P mole. For this particular reaction, if I consider here to be my forward reaction and I consider here to be my backward reaction, the rate at which this forward reaction occurs must be equal to the rate at which the backward reaction occurs. And whenever I talk about rate of reaction, in case you don't know before, there must be a constant that we call the rate constant. So let me put K, rate constant K, but then there will be a confusion. Because there are two reactions here. If I now say the rate constant, or if I say rate of reaction, somebody should be confused. Because you should be able to ask me, are you talking about rate of forward reaction, or you are talking about the rate of backward reaction? If I am talking about rate of forward reaction, I should write rate of forward. Then, if I am talking about rate of backward reaction, I should say rate of backward. Then, if I am going to have a constant as well, called equilibrium constant, I should be able to have equilibrium constant for the forward reaction. Then what would you say? I must be able to have equilibrium constant also for the what? For the backward reaction. This makes a lot of sense. Then we now want to look at something else again. And what we want to look at now is, there is a fact. If reaction will occur, the rate of chemical reaction depends on concentration of the molecules. For instance, let me quickly give you a fast illustration. I have the following molecules here. In this container, I now multiply the number of molecules. When do you think the reaction will occur faster? Of course, here. Why? Because there are more molecules and the rate of the collision will increase based on Arrhenius theory. So these people will collide faster and more than the rate at which these people will collide. So the rate of chemical reaction depends on how much are we concentrated. So that means concentration of the reactant is a factor for the rate of chemical reaction. So therefore, we believe that this thing should be even called the rate law. So according to rate law states that the rate of chemical reaction is directly proportional to the concentration of the reactant molecules raised to a certain power. And this power is what we call order of the reaction. So let's try to look at this law. Let's put this law into mathematical expression. The law says that the rate R of a chemical reaction is directly proportional to what? Is directly proportional to what? To the concentration. So if the rate is proportional to the concentration, then I can now say that rate of a reaction is proportional to this symbol for concentration. Concentration is proportional to the concentration raised to a certain power. If I don't know. So let's look at this reaction that we have here. I can say that the rate of reaction, somebody will ask me, are you talking about forward or backward reaction? Here I am talking about my forward reaction. So the rate of my forward reaction now, that's clear, right? Is proportional to the concentration of the proportional to the product of the concentration of the reactant molecules. So product means times. Concentration of which one? A. Concentration of the other one, B, raised to certain power. So if I put X here and I have Y here, this makes a lot of sense. I can now clearly say that my rate of forward reaction equals to, I want to introduce my constant, but my constant will still be the special constant called the rate constant for the forward reaction. So what will I have here? A, I'll put X, then what will I have here? I'll have B, then I'll put Y. So this is the expression for the rate of forward reaction. I want us to now also create the same thing for the backward reaction. Meaning that we are taking this and this to be our reactant now for the backward reaction. So for the backward reaction, we're going to have the rate. Okay, let me use another color for that. In that case, I'm going to have the rate of my backward reaction proportional to the product of the concentration C and concentration D to certain power Z and P. I want to introduce my equality sign now. So the rate of backward reaction will now be equal to K concentration C raised to Z concentration D raised to P. This is the expression for the rate of the backward reaction, and this is the expression for the rate of the forward reaction. Can you remember what we said we want to pay our attention very close to? That we said we want to pay our attention close to something that we call a condition for a system to be in chemical equilibrium. And that condition is that the rate of the forward reaction must be equal to the rate of the backward reaction. So if rate of forward reaction equals to rate of backward reaction, what is rate of forward reaction? This is what we call rate of forward reaction, and this is rate of backward reaction. So can we try to join them? So that means that here I'm going to have Kf, concentration of A, power of X, concentration of B, power of Y, equals to what is the rate of backward reaction? K backward, I didn't remember to put that. K backward, then concentration of C, power of Z, concentration of D, then power of P. If I can successfully write this equation, then I am already having two constants in this expression. Constant for the forward and constant for the backward. All I need to do now is to now express these two constants as one. I am going to look for their ratio, and I'm going to call it that one. The overall constant, I have one constant, another constant. What is now the overall constant for this chemical equilibrium? The overall constant, equilibrium constant, is always given by constant for forward divided by constant for backward. The equilibrium constant is now equals to what is constant for forward? Constant for forward over constant for backward. Okay? Let's look up for how we can bring this up and bring this down. It's simple. Can you try to imagine that you're having K forward over, K forward equal, K forward times R equals to K backward times M. Can you write that K forward over K backward equals to, you look what is up here, what does it matter? That guy will stay down, so that when you cross multiply you get this back. So R should be down, M should be up. If I cross multiply, I'll still get my K backward times M equals to K forward times R. So we are going to do the same thing here to make this expression easy. So what is K forward? That means from this expression, I want K forward to be up and I want K backward to be down. It will now be equals to, who are the relative of K forward? The relatives of K forward will be who and who? A and B, right? So they should stay way down. Who are the relative of K backward? C and D, they should stay up. Such that when I cross multiply, I get the same expression back. So I am going to have C raised power Z, then D raised power P, divided by A raised power X, then B raised power Y. So this is how we write expression for equilibrium constant. So you can see that whatever is on the right hand side, we stay here. And whatever is on the left hand side, we stay up. Left hand side, right hand side, then left hand side. So if I want to write an expression for chemical equilibrium, I say right hand side over left hand side. But then, will you have to do that? There is a condition. Every time you want to write, you check for the state of the matter that you want to write. Anything that is in solid state, you must never write it in the chemical equilibrium. Anything that is in liquid state, you must never write them. The only two people that you write are gases and aqueous. These are the only two that you must write. Don't write this, but always remember to include it. What would I do if I have solid and liquid? For instance, let me assume that here is solid, and here is liquid, and here is liquid. How will I write this expression now? We said forward over backward, right? So I am going to say K equilibrium equals to what is on the right hand side? C and D are me. But the two of them, they are liquid and liquid, and I must never include liquid or solid. So at their place, I will write 1. What about down? What is here? A solid. I won't write that. I will replace it with 1. What about the other one? The other one, we said that one should be in, Okay, let's say this one is in gaseous state. So it's only B that will enter this equilibrium now, since every other person are not normal. So this is just equilibrium expression for this simple thing. So we should pay attention to that. Now look at this equilibrium constant that we call overall equilibrium constant. It is not affected by anything. The only factor that will affect it, that will change it, is temperature. Please pay attention to that. Nothing will affect equilibrium constant. It always changes. It always adjusts itself. But temperature can kill him. Temperature can injure him. So now we are going to look at some of the questions that are commonly asked under a chemical equilibrium for a system that is in equilibrium. But before we are able to answer those questions, we need to have idea about one or two things. And those things are: one, Le Chatelier's principle. There was a Frenchman that we call Henri Le Chatelier. According to Henri Le Chatelier, he told us that if a system is already in equilibrium, it's already in equilibrium. Nothing will change that. If you try to do anything, maybe you impose any factor on him, maybe you press him down, it will adjust. It's going to adjust himself. Then if you push him forward, it will bring himself a bit backward. Whatever you do to a system that is in equilibrium, it will adjust itself so that the equilibrium is not disturbed. So for a system in equilibrium, according to Le Chatelier, the factors that we can impose on them, they include pressure. But this pressure, we can only impose pressure on gas. If we don't have gas, pressure has no effect. Then we can have something that we call concentration. We can also impose this concentration on them. Then we can also try to change temperature for them. And what other things can we do? So if you are changing volume, volume is also like, volume will affect pressure based on something that we refer to as Boyle's law. You can remember. So let's look at how does all these factors, how do they affect a system that is already in equilibrium? I want to remind you that no two substances on earth can have the same temperature. Can have the same heat content. For instance, let's say I have CO2 and the heat content is 100 joules. If I want to turn CO2 to CO3 or there's no CO3. CO3 can never have 100 joules. It's either it has more or it has less. If this guy, for instance, have 80 joules, this reaction can never ever occur unless I remove heat from this guy. If I remove heat from this guy, since I subtract, I will write like this. The heat that I removed from the guy, I will throw it to the surrounding. The surrounding will be hot because I've given them heat. I remove heat from here. That's why this happened. How much heat will I remove? 20 joules. Where will I put them? Surroundings. Therefore, that reaction, it only proceeds when I remove heat. I will therefore call it exothermic reaction, where the word thermal means heat and the word exo means outside. So I have removed heat. I think you know what happens next. Imagine that I am having CO and I want to turn this CO to CO2. Probably if the heat of CO is 80 joules and this guy is 100 joules, this reaction can never occur unless I am able to add heat to him. And how many joules will I need to add like that? 20 joules, right? If you don't add 20 to this guy, it can never turn to this 100. Where will you get that 20 that you are adding? From the surrounding. We draw heat from the surrounding, and the surrounding starts feeling cool. When you remove heat from them, they start acting cool. So this kind of reaction, I have added heat. I call it what? Endothermic reaction. You can see that if this reaction were to be a reversible reaction, in the forward reaction here, from left to right, do I have to remove heat or I may add heat? You can see I have to add heat. So therefore, it's I have to remove heat. Therefore, it's an exothermic reaction. Do you think about you coming back from here to here if it were to be a reversible reaction? What will you do before 80 can turn to 100? You have to add it energy. So that means a reaction that is endothermic in one direction will be exo in the other direction. So that means that if I actually want to go from here to here, what pace is that this place have a lower heat, so I have to remove some away. So removal of heat will favor here. But if I increase temperature, this is the side that like more heat, so this side will be favored. The reaction can shift forward or shift backward. So how do we now recognize where a reaction will shift to? It depends on what they are doing. So let's look at effect of temperature as we have started. For a system that is already in equilibrium, let me quickly talk about other process. Let me have a simple question to use as for other process. So okay. So let me look for a question on other process.
The equilibrium concentration of the ammonia.
So this starting. We have here. Should remember that. What must of me know? Should be ready. Should be ready.
Go.
So in this reaction that we have here, this industrial separation of ammonia gas from hydrogen and nitrogen, and this reaction is it endothermic or exothermic? It's negative heat, so it's an exothermic. The meaning is that if I am going from here to here, I must remove 92 kilojoules before this reaction will occur. But what about if I am coming from here to here? What should I do? And that means I must add 92 kilojoules before the reaction will occur. And if that's true, that means that in this direction, the reaction is what? Exothermic. Why in this direction, the reaction is what? Is endothermic. Now, let me now ask you a question. You remember that the whole reaction is occurring in a particular container. If the temperature of the system is now increased, which direction will be favored? Then you think. If I here, does from here to here want me to, so if you look at the reaction, so that means if I increase temperature of the system here, if I increase temperature, does this direction want me to increase temperature? No, it wants me to remove. What about this direction? Yes, it wants me to add heat. So if I increase temperature of the system, this side will be favored. When I say this side is favored, okay. So the backward reaction that we have here, if I increase temperature of the system, it will favor the backward reaction because the backward reaction wants me to increase temperature. What about if I reduce temperature automatically? The side that want me to remove heat will be favored. Here wants me to remove heat. So this direction will be favored. And when I say here is favored or that place is favored, if here is favored, anybody here will increase. For instance, they can ask questions. How can I increase the production of nitrogen? If I want more of nitrogen, what should I do? Should I increase temperature or decrease temperature? Where is that guy they're asking you about? Is it on the right hand side or on the left hand side? It's on the left hand side. What does left hand side want? It wants me to do what? To add or remove heat. It wants me to add heat, right? So increase in temperature, we add more heat. So that will favor the left hand side. And whatever favor the left hand side will favor this guy. It also favor this hydrogen. Whatever favors this side will favor the ammonia or any other person that is here. So therefore, increase in temperature will favor the production of hydrogen. It will also favor the production of nitrogen. So that is the solution to that here. So now let me quickly explain the other two concepts. The idea of pressure. Let me start with concentration. When we talk about concentration is telling us about how many of you do we have here, how many of these do we have here, how many of these do we have here. In the course of concentration, let me change these guys to another substance and put aqueous. Then aqueous, then aqueous. If you look at the reaction that I have here, I just made that assumption, though they are gases, but I just use them as illustrations. According to what I have here now, the concentration here, here, and here, if this system is already balanced and it's already in equilibrium, I can make here to get increase in temperature. I can also make here to be increased. I can make here to be decreased. I can make here to be decreased. But what this chemical is conscious of is that it doesn't want this place to be more than this place, and it does not want here to be more than here. So let's try something. Let's assume that I go and carry nitrogen from US and I pour more nitrogen here. If I pour more nitrogen here, what do you think I have done to the left hand side? I have increased the people that are there. Chemicals have pity for each other. So the chemical here feel like we are much and this guy is small because they have increased one of us, so here we are more now. So what will happen is that we will shift some here, so here will be favored. We will give more to this place. Now let's think about it again. Let's assume that you add more hydrogen to this place. What will happen to the left hand side? You have increased their concentration. What will they do? They will feel pity for the other side and they will pour more there. So increase in concentration from here will favor whatever is here. Let's look at another situation again. Let's say as I produce the ammonia, I start withdrawing them away. I take some ammonia away. If I take some ammonia away, this place is now less, this place is now more. The people that are more still feel like this guy is suffering. Let's go and help him. So they pour more of their own content here. So in short, the idea of concentration is that if you in anywhere that is big, favor the side that is small. Anywhere that is small, get favored. What about if I add more nitrogen to the system, more ammonia to the system? What will happen? It will favor the backward reaction because here is already much, so it will favor the side with small. What if I withdraw some hydrogen from here? If I withdraw some hydrogen, what do you think will happen? This side is now small. This side will now pity them that, oh, they are smaller than what they used to be. Let's go and help them. They will now pour some here. So that means that idea of concentration is either you add more or you remove from somewhere. If I increase here, it will have the same effect as reducing here. If I increase here, it will have the same effect as reducing here. So that's all about concentration. So let's quickly look at pressure. If I have gas here, which is the normal thing that we are meant to have, I only use the other one to do explanation. If I have gas here as a normal herbal process, what is going to happen if I increase pressure of the whole system? Remember, they are all in one container. If I increase pressure of the whole system, what effect will it have? If I reduce pressure of the whole system, what effect will it have? Remember that whatever happens to pressure, opposite is happening to volume. They might give you exam question in terms of volume and not pressure. But let's learn pressure, then use opposite for volume. If you look at the left hand side, all the gases that I have there, this guy is a gas. How many does he have here? 1. This guy is also a gas. What does he have here? As there, this mole is 3. So that means that the total gas I'm having on the left hand side is how many? While on the right hand side, the total gas I have here is how many? Is 2. You can see that the gas here is more than the gas here. If the gases are not equal, pressure will affect. But if the gas here is gas here, pressure cannot have effect. It's already balanced. Now that we have more gas here than here, if I increase pressure of this system, the side that is small will be favored. Increase pressure, help small side. Reduce pressure, help big size. So if whatever you do to pressure, it will just get the number. We have increased pressure now. Increase pressure, will it favor the side that is increased? No, it's favor opposite. Increase in pressure will favor the side that has small number. Then if you reduce pressure, it will favor the side that have bigger number. That's just the concept of pressure. Why volume is opposite. But then let's look at this illustration. Okay, let me still leave it. Increase in pressure will now favor which side here now? It will favor production of ammonia. Increase in pressure will favor pressure of ammonia. Increase pressure, small side. Reduce pressure, big side. If I decrease pressure of the system, where will it favor? The side that is big. If they now ask me a question as volume, I will first calm down and take the question to pressure and answer in terms of pressure. For instance, they want to ask me a question about volume and pressure. What they can say is that, imagine I drink gari. There's a food in my village called gari. I pour gari in water, we soak it in water. Then this gari gets swollen most times. But I still need water to be there, but then there's no way for the water to be there. In every household in Nigeria, there is always a kind of plastic that is big under everybody's chair and bed. Midnight, when they can't go out, they bring it out and pour some content inside, like urea mixed with water. During the day, they pour it outside. If you pass that place that morning, you will receive blessing of smell and delight. Then I go out to buy groundnut for my friend who has visited to drink this called gari. But then the guy discovered that the gari is from a Gibbs land, and the gari expands so well that he is unable to take it out of this small cup. Then the guy saw this big plastic rubber under my bed, and the guy feel like, wow, this will be better, I can pour more water. And the guy poured the content of the gari here. What has this guy done? He has increased the volume. He has decreased the pressure. So think about that. So this is another way they can ask us. If you pour something from small container to a bigger container, you have increased volume. An increase in volume is decrease in pressure. If you remember Robert Boyle. One, if I pour from a bigger container to a smaller container, I have reduced volume or I have increased pressure. So if they tell me now that they increase volume, what will I learn? I mean they reduce pressure. If they tell me they reduce volume, what did they do? They increase pressure. If they reduce volume, they increase pressure. If they increase volume, they reduce pressure. Whatever they do to volume, opposite is pressure. Then your question can be answered as pressure. For pressure, the side that is big is only favored when you lower pressure. Opposite. The side that is small is favored when you increase your pressure. This is how we answer questions under chemical equilibrium. So now I'm going to answer like 3-4 questions now for you to see how our pressure, our temperature, and our volume can affect the direction or shift in equilibrium. Then I also told you that the only thing that will affect our equilibrium constant, the value, is temperature and nothing else. So now let me ask some questions. Okay, so question 1. The very first question I'm going to solve here. Yeah, let's ask some questions. Okay?
Okay. Ammonia. Other process.
Other process. Ammonia.
N2.
Okay, N2.
Gaseous.
Gaseous plus
3H2.
3 hydrogen gas. Reversible reaction.
Ammonia.
NH3. Then we have to, it's also a gas. Okay?
Change in history equals negative 92 kilojoules.
Change in
enthalpy.
Okay, enthalpy change. Now, change in enthalpy equals to
minus 92 kilojoule.
Minus 92 kilojoule. This is an exothermic in forward direction. So that means in backward direction is going to be what? An endothermic. Okay?
The equilibrium concentration of the ammonia.
The equilibrium concentration of the ammonia
will increase if
what would you have done to increase this ammonia that is here? Number 1, do you think you should increase temperature? If you increase temperature, this guy will be reduced and more of this guy will be produced, because increased temperature will favor this side that is plus, that is asking you to add heat. But a decrease in temperature will help you, right? Why the other thing that will help you? How many gas do you have here? We are having 4 gases, 1 and 3. Why here we are having 2? What will favor this side? Increase in pressure and decrease in temperature. So let's add the options that we have.
A catalyst is introduced into the system.
Alright, thank you. Whenever we use a catalyst for a system that is in equilibrium, the catalyst will help here and help here equally. Just like when you and your cousin are fighting, and your classmates mistakenly come and catch you people, they will help you to play a role that you should fight very well. So they will help A and they will help B. They give you cutlass, they give your cousin cutlass too. So that means a catalyst does not favor any side during chemical equilibrium. What a catalyst does is to lower the activation energy and make the equilibrium to be attained faster. Okay? So that means option A can never be correct, right? So now option B.
The pressure decreases.
If I lower the pressure, if I reduce pressure, this side will be favored. Because a side with large value, lower pressure. A side with big value, a site with small value, higher pressure. So option B is also wrong because of that pressure. Okay, C.
The temperature decreases.
If I lower the temperature, here will be favored. So the ammonia production is favored. That one is correct.
Option D.
Option
The temperature increases.
If I increase temperature, here will still be favored. So the correct option there is option C. Okay? Another one.
Okay, in the equilibrium reaction
In the equilibrium reaction
of SO2
SO2
plus oxygen gas
plus oxygen gas
to give
to give
2SO3.
2SO3. This is contact process. This is contact process. The production of H2SO4. Okay?
Gaseous, everything in gaseous.
Okay, everything in gaseous state. Okay?
Then sodium.
Then
Balance.
okay. Yeah. Okay, that's balance. Okay?
The role of the vanadium 4 oxide is.
Okay, we are using vanadium 5 oxide in this kind of reaction. The vanadium 5 oxide is a catalyst. And what will a catalyst do to such a reaction? It will make the equilibrium to be attained faster. So this vanadium 5 oxide, its role is to allow us to attain the equilibrium as soon as possible. It will not favor any side here. Though that must be a wrong question coming into equilibrium constant, but then it's correct. So the function of the vanadium 5 oxide is to serve as a what? As a catalyst. Okay? Yeah, next.
Okay. The position of the equilibrium of an exothermic reaction.
The position of
equilibrium
of
an exothermic reaction.
Of an
Exothermic reaction.
exothermic reaction. If I say exothermic, that means exo means outside, thermal means heat. The removal of heat, of an exothermic reaction
Can be shifted forward by.
Can be shifted forward by how can you shift the position of an exothermic reaction forward? What does exo want me to do? Let's assume I have A and it's giving me B, and this guy is exo. Exo means I should do what? Remove heat. Remember in chemical equilibrium, here is taken forward, right, and here is taken to be backward, left. So how can I shift the equilibrium forward to the right for an exothermic reaction? What does it want me to do? Remove heat. Are you now? What are the options? Option A?
Increase pressure at constant temperature.
If I increase pressure and I keep temperature constant, I don't need pressure here because it doesn't tell anything about gas. And then if I keep temperature constant, it does not make sense. The reaction will not shift. Okay, B?
Decrease pressure at constant temperature.
I don't need pressure at all. If I keep temperature constant, it doesn't still work.
Increase temperature at constant
If I increase temperature, my reaction will shift backward because backward will be endo. Backward wants heat. If I increase temperature, backward will favor. For me to favor forward, option D.
Decrease temperature at constant pressure.
If I decrease temperature, here is favored, and I do not change my pressure, it makes a lot of sense. Next one.
If an equilibrium reaction has change in enthalpy to B.
If an equilibrium reaction has change in enthalpy to B
greater than 0. The reaction will favor.
If an equilibrium reaction has change in enthalpy to be greater than 0, what is greater than 0 is positive. Are you now? If it's greater than 0, then the reaction will only be favored when I do what? When I add heat. Are you now? When I add heat energy or when I increase my temperature, that's when it will favor this particular reaction. So let's do two more and end the class. Then you are advised to solve plenty questions and give us comments on whatever you get. You can ask questions in our comment section as well. And let's see how many of these things explained you can remember. So question next.
Production of iron.
Yeah?
F is solid. plus 4H2O gas
plus 4H2O gas
to give Fe3O4 solid.
Fe3O4
solid
is solid
plus 4H2 gas.
4H2 gas.
The yield of hydrogen in the above reaction
The yield of hydrogen in the above reaction
is increased by.
Now, if you look at the reaction that I have here now, this guy is a solid now. Did they put any temperature? No. They didn't tell me maybe endothermic or exothermic. So temperature is out of the discussion. But then, if I look at what is here is a solid. What is here is a gas. So there are 4 gas here. If I look at what is here is also a what? A gas. 4 gas. If I have 4 gas, pressure have no effect. Fine. We have options.
Decreasing the pressure of.
Oh, sorry. What's the question again?
The yield of hydrogen in the above reaction.
The yield of hydrogen in the above reaction
is increased by.
Is increased. We are looking for what we favor forward reaction because hydrogen is in the forward. Okay, it's increased by.
Decreasing the pressure of the system.
Pressure does not have any effect. You can see. We have option B.
Decreasing the amount of the steam passed.
Decreasing the
amount of the steam passed.
Of the
steam.
Okay, of the steam passed. This is the steam. If I reduce the amount of the steam that I'm using, remember we have to pass steam over ion fining in order for us to have this compound and this gas produced. So if I reduce the amount of this guy, immediately I reduce the amount of this guy, left hand side is suffering because I have reduced them. Right hand side start beating them and flow more here. So things here will be favored. This direction will be favored. More ion, more steam will be produced. If I lower anybody, so that's not correct. But we are looking for what we favor this guy. Okay?
Removing hydrogen from the system.
If I start removing hydrogen from the system, what do you think is happening to the right hand side now? They are smaller. And the left hand side start beating them. And the reaction shifts to the right hand side. Then that is the correct answer, right? Okay, yeah.
Removing some iron from the system.
If I remove some iron from the system, what do you think is going to happen? The left hand side is going to be favored. If I reduce concentration of the iron, left hand side will be favored. So thank you very much. We advise you to solve a lot of questions on your own. We meet again in our next video. Remember to like our video, try to comment, try to solve problems, give us, tell your friends, share our videos, and try to subscribe to our channel. When you do that, we'll be impressed and we'll make more videos that are reasonable. You can also make requests and tell us what exactly you want us to do for you. We understand what the cause signs. Thank you.